Okay, let's start chapter 4. We talk about section 4.1, continuity of a function. Definition. Let D be a subset of R and f is a function from D to R. Then f is continuous at A. This is a point in D, or I occasionally write x equal to A belong to D. This is how the book writes, and this is how I usually write. If for any given positive numbers epsilon, there exists a number delta positive such that fx minus fa less than epsilon, provided that x minus a less than delta and x belong to D. So from this definition, you can connect it with what you learned in chapter 3 about limit of a function at a real number. Then you can pretty easily see that if f is continuous at x equal to A, if and only if limit of fx x go to A equals fa. Okay. So the definition over here, it just means that the limit of the function fx is just the number fa over here. Right? In the definition of the limit that we presented in chapter 3, then the limit is the number L, but in this case L is replaced by fa, which is the limit of the function. So this equation can be rewritten as f of fx up goes to A equal to f, and this limit of x go to A. So because A over here is nothing but just limit of x and x go to A, so we can replace it over here. So just the same thing, but two different ways to write it. And what does it mean by this equation? It just tells us that we can take the limit inside a continuous function. What this means is can move the limit into inside of a continuous function at the given point. Okay, so limit outside, you can move it in. Yeah. And geometrically, the function f is continuous at the point x equal to A if the graph the point A over here So this is fa, and it's equal to the limit of the function at x go to approach point A. Okay. Then the function also approach the value fa here. Okay. So the function doesn't have a jump at that point, basically. That's what you can think of. The continuity of the function at the point x equal to a. Now example. The polynomial px, which is cn xn, cn minus 1, xn minus 1, and so on, c1x plus c0, is continuous. At any point A belong to the set of a real number R. Proof. We use the observation that I wrote down over here to prove it. Okay. So f is continuous if and only if this limit equal to fa, right? So to prove that p is continuous, we need so given any number, real number A, we need to prove limit of px x approach A equals pa. Okay. Indeed, in the previous lecture, I told you a few rules of limit, and now you can use them. So limit px x approach A will be equal to limit of cn xn plus so on c1x plus c0, and you can use the rule of sum of limit. Sum limit of sum equal to sum of limit, so it's just equal to limit of cn xn and x approach A plus so on, and limit c1x approach A plus limit of c0 approach A. And now the limit of a constant of some function equal to the constant of limit. So we can take that constant now, and this limit of x power n approach A and plus c1 out, then c1 limit of x approach A x, and then this just c0. And now we use the rule of power. Limit of power is equal to power of limit, so it's just limit of x and then power n plus so on c1, and limit of x at x approach A, we easily know that it's just A c0. And again, remember this one is just A, so it would be equal cn A power n plus so on c1a plus c0, and this exactly pa. So we finished the proof.